Hey everybody, welcome back. So I'm just going to jump right in. We were talking about the normal distribution in the last video. So we would have some kind of random variable. X is a continuous random variable. And if we said that X followed the normal distribution, we would use this notation. And there were two pieces of information we would have to give with the normal distribution. We would need to tell you what is the mean and what is the standard deviation, right? And these normal distributions, though they all are a little bit different, have a characteristic shape, right? The peak is always at the mean, and then the standard deviation tells us how tall or wide it is, right? When we have a smaller standard deviation, we might get something, right? A similar shape, a little bit narrower, but also a little bit taller, something like that, right? And if we made a much larger standard deviation, we might get something that looked more like this, okay? So, and in all these cases, we would use, just redraw it, we still use area to represent probability, right? So if I have my distribution and I ask something like, what's the probability of being between A and B? These are two data values, maybe they're up here, then the result will be the area of this segment between those two values. Okay, so we talked last time about how to get those values. We usually use calculators. You might even find yourself in a situation where using a table might work. I mean, it will work. It might be easier than a calculator if you happen to have one. But in any event, we don't have to do the calculus that is necessary to compute these kinds of areas. So I want to look at another idea that won't seem related at first necessarily, or only a little bit related, but then we'll see how this is all going to pull back into another big piece of this whole puzzle. So I looked up some data and found a study from a region of Spain, the Andalusia region, and suppose, and they had this information. Okay, so they had two pieces or two studies. We're gonna have two random variables. The one is the weight of a 3-year-old female, and it's in kilograms. And in this study, N was 90, meaning the number of subjects studied was 90. And they found that the weights were distributed normally with a mean of 14.9 kilograms and a standard deviation of 1.70 kilograms. Okay, and in the same study, they looked at all ages across the population, and they had weight of 7-year-old female, again in kilograms. In this case, they had 116 for the sample size. And again, they found a normal distribution, and now the weight was, the mean weight was 25.5 kilograms with a standard deviation of 5.67 kilograms. Okay, so there's our two distributions. Suppose we, maybe these are your children and you have a 3-year-old female who weighs 12.9 kilograms and a 7-year-old female weighing 21.2 kilograms. Okay, so let's notice a couple things. Both of them are a bit under the mean, right? So here we're going to say 2 kilograms below mean, right, for the 3-year-old. And our 7-year-old is, let's see, what was the mean? 25.5. So the 7-year-old is 4.3 kilograms below the mean. Okay, so they're both a little bit below the mean. And a question we might ask is, well, which of these two children is more, let's say, extreme, right? Not that either of these are extreme situations, but just which one is more different than the mean, right? Obviously, the 7-year-old is more kilograms below the mean, but I think it's also obvious 4 kilograms might not mean as much to a 7-year-old as to a 3-year-old, right? It's a much smaller part of the whole, right? Relatively speaking, it might not be as much, okay? So here's a way we can measure how far they are. We can talk about their distance from the mean in units of standard deviations. Okay, so let's compute this in a moment, but let's do a little bit of work to see how we might compute it. So let's see, let's make a little space. I'll erase some things over here. All right, so let's think about just units in general for a minute. So if I had something like 12, if I knew something was 12 feet long, okay, let's just do this. Let's say I had something that's 12 feet long, and I wanted it in units of yards. One thing I can do is divide by how many feet are in 1 yard, right? So there's 3 feet in a yard, so 12 feet becomes 4 yards, right? If we wanted to convert to yards, we divide 3 feet by how many feet are in each of these units, right? Well, we're going to do the same thing here. We're going to take our distance from the mean in, let's say this, in data units, and we'll divide by how many data units in a standard deviation, right? So if here's our mean, and here's my data point, right? I'll look at how far away this is, right? And then I'll see how many standard deviations can I fit in here, right? If it was 10 units away and a standard deviation was 2 of those units, we could fit 5 of them in there, okay? Well, what is this distance? How do you find the difference between two numbers? How far away something is from the mean? I would take the mean minus the data. Sorry, I'm going to do I want to know, sorry, I said that backwards. We're going to do the data minus the mean, and I'll say a little more why we do it in that particular order in 1 second. We're going to do the data minus the mean to find out how far away it is, okay? And a little bit more. That's what I'll say in a moment when we finish this example. And then we can divide that, right? How many data units are in a standard deviation? That's what the standard deviation is, right? Look at these standard deviations. Their units are the same as the data. So it's 1.70 kilograms is a standard deviation. So it takes 1.7 kilograms to make 1 standard deviation. So I'm going to divide by that number, okay? So that's what we're doing here. Let's do this, and then we'll talk about for these two values, and then we'll talk about the order and things like that. So we're going to take the data value. Let's start with the 3-year-old, 12.9 kilograms minus 14.9 kilograms gives me -2 kilograms, okay? And this is why the order matters. The way I've ordered it, not only do I know I'm 2 kilograms away, but the negative tells me that I'm below the mean, right? So if we take the data minus the mean, if the data is below the mean, it'll be negative. If the data is larger than the mean, if it's above, this will be positive. So it tells us not just how far, but in what direction. And then we can take that -2 kilograms and divide it by the standard deviation, which, remember, up here in our X random variable, we're told it's 1.7 kilograms. Notice the units will cancel. We get negative 1.18. It's just a number that counts the number of standard deviations. In other words, 12.9 kilograms is 1.18 standard deviations below the mean. Okay. Remember, one way we can think about a standard deviation, it's not entirely precise, but it's a reasonable idea in your head, is it's how far from the mean is the typical piece of data. So the typical piece of data is one of these from the mean, more or less, and we're a little bit more than that, right, in the negative direction. Let's do the same thing for the 7-year-old. We take the data value of 21.2 minus the mean, 25.5, right, because now I'm looking at the y. And what did we say that was? Negative 4.3 kilograms. And we will take negative 4.3 kilograms, divide it by the standard deviation of the y random variable. That's 5.67. Again, standard deviation is always in the units of the data. We get negative 0.76. Okay, so this is how far below the negative 1.18 is how far below the 2-year-old is in terms of standard deviations, and this is how far below the 7-year-old is in terms of standard deviations. So the 7-year-old, while below the mean, is less far from the mean than the typical piece of data, right? Or less than the average distance from the mean. Again, not a precise way to think about the standard deviation, but a good one. Whereas the 2-year-old's a little more than the typical standard deviation, a little more than the typical data point from the mean. And so in terms of standard deviations, we would say it's further away, okay? And this is a pretty good way to compare data across different data sets, which is a very difficult thing to do, right? Here, at least, they're the same weight, but we can imagine we could compare things like heights and weights, which are very difficult to compare, right? What's more, 5 pounds or 3 feet, right? It's not a reasonable comparison. There's no way to really compare them, but we can compare the things in standard deviation to understand how they are in relation to the other data in that set. Okay. So this kind of comparison is a pretty common one, and we give this thing a name, right? So this computation that we just did is something we call a Z-score. Okay, so let me write out what we did. A Z-score is equal to the data value minus the mean divided by the standard deviation, right? That's what we did in these steps down here. We subtracted the mean from the data value, then divided by the standard deviation, which is what this thing says. So we can write this in a compact formula. Z is equal to the data value, I'll call X, minus the mean if we're dealing with a population, over the standard deviation. That's our mean and our standard deviation, mu and sigma. If we're looking at a sample, we might write X bar over S, right? But in either case, they're doing exactly the same thing. This top definition is exactly what we do. Our data value minus the mean divided by the standard deviation, okay? And that is what's called a Z-score. And a Z-score is a pretty fundamental thing that we are going to be computing over and over and over again as we move forward. Okay, so let's do a couple of other things. Something interesting happens with these Z-scores, okay? So one thing we can do, we can convert all data to a Z-score, right? I could take every possible weight, right, and convert them to a Z-score. Right? What this does is it changes our distribution from a distribution of weights. We get a distribution of Z-scores. Okay? And what this distribution will have, well, let's take a look at it and see what see if we can kind of clarify what I'm trying to say here. Let me share something different. Let's look at, let's clear these drawings. Okay. So let's see, we've got, let me turn this off for a second. Okay, so here's a normal distribution, right? This happens to be the one with a mean of, right now it's at 6.7, and S, the standard deviation is 1.47, right? So what's going to happen if I convert all this data to z-scores? Well, remember my z-score formula. I take a data point and I subtract the mean and I divide by the standard deviation. Let's use sigma for this. So suppose my data value is the mean, right? That's one of the data values. If I take the z-score of the data value, I get the mean minus the mean divided by the standard deviation. Well, that's just 0. Okay. What if my data value is one standard deviation above the mean? In other words, it's the mean plus the standard deviation, right? Or mu plus sigma. So that's now my x value. Well, let's take the z-score for that. Instead of putting in x, I'm putting in mu plus the standard deviation minus mu, right? There's x, there's mu, divided by the standard deviation. That's just the standard deviation divided by the standard deviation. That's equal to 1. Okay? In other words, this new distribution, the mean becomes 0 and the standard deviation becomes 1, right? This piece of data, the mean plus 1 standard deviation, was like the typical distance from the mean, right? 1 standard deviation above. Well, it's now 1 unit above the mean. So the new standard deviation is 1. So that's the new distribution we get. Let's look at that in this graph. Oops, went the wrong way. So what I'm going to do is change my standard deviation to 1. In this case, it gets a little bit taller. And then I'm going to move the mean until it's at 0. And so we've moved all the data over here, right? We had to change the shape a little bit to adjust the standard deviation, and we get this new distribution. So why would we want to do this? Well, let's do one more thing while we move it. So let me move back somewhere. Here's some arbitrary distribution. Let's say I have a standard deviation of 1.9. Suppose I was computing the probability between these two values here, right? So somewhere between 4 and 5 and somewhere between 7 and 8, okay? I've made this so these two values are a half a standard deviation below the mean of this graph and 1.2 standard deviations above. In other words, this point right here is the mean plus 1.2 standard deviations. This point here is the mean minus half a standard deviation. Okay, those are what those two data values are, right? If you computed, right, the mean of this one is 5.4 and the standard deviation is 1.9. If you put those in here, you'll get these two numbers. As I convert to z-scores, meaning change the mean to 0, right? Do that process that we did up here, but we do it for every data value. The mean is going to move to 0. The standard deviation becomes 1. Let's watch what happens to this area, which would represent the probability of being between these two values. As I move the mean, so I'm changing the mean from 5.4 to 0, notice the shape does not change. In other words, that area is exactly the same, right? So again, these two data values I'm looking at now, something seems a little bit off. Oh, that's right, sorry. I haven't changed it to 1 yet. These two data values, this is still a half a standard deviation below the mean. My standard deviation is 1.9, so it's just a little less than 1 unit below. And this one's up above by 1.2 standard deviations, where a standard deviation is 1.9, so we're a little bigger than 1.9 away. Now, if I change the standard deviation to 1, right, converting to these z-scores, notice those, as the standard deviation gets smaller, those values get closer, because if one is half a standard deviation below and the standard deviation is getting smaller, it must be getting closer. But at the same time, my graph is getting taller, right? And what happens is the area stays the same, even though the shape has changed, right? If you look at this last thing in the column on the left, this is some calculus. You don't need to worry about what's happening there, but what it's doing is computing the area. And notice as I change the standard deviation, that area does not change, that 0.576392791052, right? That doesn't change as I change the standard deviation. So as it gets wider, it gets shorter. As it gets narrower, it gets taller. And so those two actions conspire to keep the total area exactly the same in both cases, okay? So we give this distribution, it's a normal distribution with, let's write this down, it's a normal distribution with a mean of 0 and a standard deviation of 1. We give it a name. Sometimes we use a capital Z. Right? And we call this the standard normal distribution. Okay? And one of the key facts is, among other things, it's a distribution of z-scores. And one of the key facts is if we convert any normal distributions to its z-scores, we can compute the probability of being between those two z-scores, and it's the same as the probability of being between those two values. In other words, if I have x is some normal distribution, and I compute the probability of x being between A and B, and if I also compute the probability of, I can take A and compute a z-score using the formula over here, right? So z sub A would be A minus mu over the standard deviation, and z sub B would be B minus mu over the standard deviation. And if I compute the probability of, on the standard normal distribution, of having z-scores between z sub A and z sub B, these are going to be equal. So if we convert to z-scores, we end up with the same probability, okay? Now, why is that important, right? Well, in the old days, it used to be important because we didn't have computers and calculators to compute these areas. And while you could do it by hand, it's time consuming. And so what they had was tables. And you can't have a table for every single standard, every single normal distribution, right? One person has a normal distribution they're curious about that has a mean of 56 and a standard deviation of 2.9, and somebody else has one with 60 for the mean and 3.2 for the standard deviation, right? You can't have a table for all the infinite possibilities, but you can have a table for the standard normal distribution with mean of 0 and a standard deviation of 1, where you can look up distributions between values on that. And so somebody working on one normal distribution can convert their data into z-scores, which is something pretty easy to do by hand, right? Just this little formula here, and then look up their probabilities in the z-score table. So then you might ask, well, we don't have to do that anymore. And that is absolutely correct. We do not have to do that anymore. However, and this is difficult to explain because we don't have enough information yet, but we are getting to a place Some of the more complicated statistical analysis we'll do down the road, several videos from now. We are going to be working with normal distributions where we don't know the mean and the standard deviation, but we might be able to use this connection to the standard normal distribution to still get information about them. And that's really as much as I can say right now. It's going to take some building up to get there. And this connection through the standard normal distribution, this connection of probabilities is really, really important. So let's do one more thing in this video. Let's go back to an example from a previous video. So let me clear what I've got here. We had done, we had in a previous video, a distribution of birth weights. I think it was birth weights in ounces. I don't remember the sample size in this, but the important part for us was it was a normal distribution with a mean of 100 and a standard deviation of 6, right? And one of the things we computed was the probability of having a birth weight between 89 and 116 ounces. Let's actually just compute that quickly again. We can go to this table, or sorry, this calculator. So I put in the mean of 100, the standard deviation of 6, and I compute between 89 and 116. And we end up with this answer down here, right? This is our answer here, 0.9628. So let's go back to the other sheet, 0.9628. All right, let's now convert these two values to z-scores. In other words, I want the z-score for 89 and the z-score for 116. So the z-score for 89 is going to be, so let's just remind ourselves, z-score is the data value minus the mean divided by the standard deviation, right? So in this case, my data value is 89. My mean is 100. My standard deviation is 6. And if you work this out, you get negative 1.83 repeater. This little repeat line above means that 3 now goes on forever. And the z-score for 116, same formula, 116 minus 100 over 6, and we get 2.6 repeater. Notice we get a negative for the value below the mean, we get a positive for the value above. 116 we can see is quite a bit further from the mean in terms of standard deviations, okay? So let's take these z-scores and let's come over to our standard normal distribution and let's ask the question, what's the probability of getting two z-scores between these two values? All right. And again, we will jump to that calculator. Okay. So I'm just going to refresh this screen just to point something else out. Notice when I refresh it, it always starts at the standard normal distribution, right? Because it's such a typical distribution for people to use. There's the mean is 0, the standard deviation is 1, and that is exactly what we want. We want to put in the values, so our z-scores were negative 1.83 repeater. I'm going to put in a couple of 3s. Wherever we stop, we're rounding it. I want to round as little as possible to make the point we're about to make. 2.6667. We'll go out to 4 decimal places in both cases, and let's recalculate. And notice this number. This 0.9628 is exactly the same value we got when we computed it directly. Okay, right? So we've got 0.9628 and 0.9628. So, like I said, in terms of computing these things, because we don't have to rely on tables anymore, it's not that important to convert to z-scores at this point in the process. However, we are going to have to rely on them later for the more interesting and complicated kinds of statistical processes we can do, where we don't actually know the distribution we're looking at, but we have this wonderful connection through the standard normal distribution. And so we want to start making this connection as clear as we can. Let's do one more thing before we go. I think I've said that several times already. I'm going to erase everything here. So this is a picture of that distribution I was just talking about. This has a mean of 100 and a standard deviation of 6. Notice the scale on the left, the Y scale, right? These numbers here, 0.02, 0.04, 0.06, right? This is only 1/10 of a unit high, where this 0.1 right here, okay? So we're very small, because remember, our whole area has to add up to 1. This is the original distribution. I want to zoom out for a second. It'll probably feel a little crazy for a moment. That thin distribution, right? So this one here is X is a normal distribution with 100 and 6. And this is our standard normal distribution with a mean of 0 and a standard deviation of 1, right? It looks very tall right now, but look, it's only going up to 0.4 because we're in this very, very small, small regime. Let me change my zoom just a little bit here. Let's just go from, let's try this. Let's see if this helps us see. Oops, that was the wrong one to change. Sorry, let me try that again. I was in the wrong place. Let's go from -10 to, okay, so we can compare them a little bit better now. So again, this one on the left is the standard normal distribution, and this one over here is the original distribution, oops, is the original distribution. I don't know how to grab that. Well, you get the idea. That's over there. And notice what has happened to the area. So that orange area is the area we computed in both cases, right? That 0.9628, right? This is between, we can see it here, it's between 89 and 116, right? That looks pretty reasonable. And we get the same thing over here between our two z-scores, -1.83 and 2.6. It's a little harder to see because of the scale, but I just want us to be able to see these two things. When we converted to z-scores, we were morphing this shape over here on the right into the shape over here, and that orange area stayed constant the whole time. Okay, that's all I'm going to say about that. That will do it for our for this video. Thanks everybody. I will see you next time.